Hello. In this video, I'll be going over the extra practice problems with the velocity versus time graphs. Before I do that, I wanted to take a minute to remind you of the basic elements of these problems. So we're going to have a velocity versus time graph, and it should look something like what we have here. What those red lines indicate is the area underneath the velocity versus time graph, and in this case, the area is equal to the displacement or the distance traveled. So oftentimes we'll need to find how far something travels, and to do that we find the area underneath the graph. The slope of this line here, because everything should be linear if we're having constant acceleration, is equal to the change in velocity over the change in time. So oftentimes we'll want to find the slope of our velocity versus time graph because that will give us the acceleration. And then the initial velocity that we're given, that is the y-intercept on the graph. The last thing I'm going to mention is that we've got these three different rearrangements here of the acceleration equation. So acceleration is change in velocity over change in time. That's just the basic slope. And then we arrange it in these other couple ways. Just solving that equation for t, we get time is change in velocity over acceleration. And solving for that for change in velocity, we get change in velocity equals acceleration times time. We use all of these at different points throughout this process. Alright, so starting on these problems. This first one here, I give you some information. It says a car is traveling 60 miles per hour and then challenges the road, and it takes 5 seconds to come to a stop. And I ask what the stopping distance is. And so the first thing here we have to look at is we've got 60 miles per hour as our speed, or our initial velocity in this case. Unfortunately, I ask you for something in feet and I give you the time in seconds. So the first step in this is actually to convert that 60 miles per hour to something that's a little bit more useful. So what we do is we take 60 miles per hour, all right, and we're going to convert it to feet per second. So we know that in 1 mile, there's 5,280 feet. And then we know also that in 1 hour, there are 60 minutes. And in 1 minute, there are 60 seconds. Go through and do all of that. You should see that things cancel out. Miles cancels out with miles. Hours cancels out with hours. Minutes cancels out with minutes, and we're left with feet per second. You do that, you should get 88 feet per second. Okay, so 88 feet per second is what we're starting with here. And then the velocity is going to go down until it comes to a stop. So this is what our velocity versus time graph looks like. It starts here at 88, all right, and then it goes down to 0. And we know that it actually takes 5 seconds for this to happen. And so this question asks for the distance traveled while it's stopping. So now that we've got these elements, the distance traveled is the area underneath the curve. So we're going to find this area here and use that to determine what the distance traveled is. This is a triangle, so it's just 1/2 base times height, which in this case is 1/2 times our base is 5, our height is 88. And if you go through and calculate that, you should get 220 feet. All right, so that one wasn't too bad aside from the conversion, which was a little bit of work. All right, here for problem number 2, it says that we have a car that's traveling an airplane that's starting from rest and is accelerating down a runway, 3.2 meters per second squared, for 32.8 seconds. It says until it finally lifts off the ground. Okay, so in this one, we have something that's starting from rest, we know. All right, and then we also know that it is going for 32.8 seconds. Okay, and this is where we have to use one of our other equations here because this is our change in velocity, all right? And so we want to figure out what this change in velocity is so we can find some other stuff out about this one, namely how far it goes. And so to find the change in velocity, we use the acceleration times time, all right, which is just another rearrangement. It's one of those three rearrangements of this equation I told you to kind of try and be familiar with at the beginning. All right, and if we've got acceleration times time, we know the acceleration is 3.2 meters per second squared, times the time, which is 32.8, and you multiply those together and you get 105 approximately. All right. So that gives us this side here is roughly 105. All right, so what we're going to do then is we're going to take 1/2 base times height again on this triangle to try and figure out what the area is. Figure out what the area of this part here is. And we get the distance traveled equals 1/2 times the base, which is 32.8, times the height, which is 105. Multiply those together, and you should get 1,722 meters. Alrighty, on to number 3 here. For number 3, what we're given here is it says there's a race car and it's accelerating from 18.5 meters per second to 46.1 meters per second in 2.47 seconds. So we're going from 18.5 up to 46.1. All right, and we know that the amount of time that took was 2.47 seconds. All right. Then the only other thing we're going to do is break this up into some shapes. All right, so I've got here some shapes that look like that. I know that the bottom part of this is 18.5. All right, the top part, if you take 46.1 minus 18.5, you get 27.6 for this part up here. This is just that part of that triangle. And then what we can do is we can figure out the acceleration from this, and we can also figure out what the distance traveled is. So for the acceleration, we're going to say acceleration equals the change in velocity over the change in time, right? Change in velocity is 27.6. It went up by 27.6 when it went from 18.5 up to 46.1. Then we divide by the time, which is 2.47. And what you get from that is something around 11.2 meters per second, or 11.2 meters per second squared. To figure out the area now, we're going to take the area of these two shapes. We've got this rectangle here and this triangle up here. And we're going to say that the distance traveled equals, we'll do the triangle first, 1/2 times 2.47 times 27.6. Now we could have done the rectangle first, it doesn't matter, we're just adding them together. So then I'll say plus the area of the rectangle, that's 18.5 by 2.47. And we get all that added together, and you should get something along the lines of 79.8 meters. Alrighty. On to problem number 4. This one says a bike accelerates uniformly from rest to a speed of 7.1 meters per second over a distance of 35.4 meters. Determine the acceleration of the bike. So in this one, we know it's accelerating from rest and it's getting faster. We don't know how much time it took, so time is unknown. We do know that it got up to 7.1 meters per second. All right, so that's that side there. All right, and so on this one, again, we're going to take advantage of the fact that, well, actually, in this one, we can just do it directly. We know this is 7.1 on this side. And so we're going to find the area here and use that to find the time. So we know that this area in here is equal to the distance traveled, which is 35.4 meters. So we know 1/2, because it's a triangle, 1/2 base times height, 1/2 times 7.1 times t equals 35.4. And solving that for t, you should get that t equals 9.97 seconds. All right. Now that we have t, we can plug that back into the acceleration equation. And you get acceleration equals change in velocity over change in time, which in this case equals 7.1 over 9.97. And you should get 0.712. And it's an acceleration, so it's got units of meters per second, or meters per second squared. Okay. Number 5. This one is getting pretty tricky now. It says that we have a train. It has an initial velocity of 20 meters per second. It says at a constant 1.8 meters per second squared. How long does it take for the train to travel 1 kilometer, and how fast would it be going at the end? So what we've got here is a train. It has an initial velocity of 20. But then since its acceleration is positive, we know that it's going to have a positive slope. So this velocity is going to keep going up as time goes by. Things that we know here, really, we just know that it's going to be going for some amount of time, which we'll call that t. And then we also know that this section here, just this part of this triangle here, is our change in velocity. All right? And I'm going to put a little set of brackets there so you can see specifically what I'm talking about. We're talking just this section here. All right? This is our change in velocity, which from those equations we know is equal to acceleration times time. This is just that rearrangement of the slope equation that I showed you right at the beginning of this video. And so knowing that you can use this is actually like really, really handy. Acceleration in this case is 1.8 meters per second squared. So this is equal to 1.8 t. All right, and then we can actually find a formula for the area here, and we know that it's traveling 1 kilometer, which is 1,000 meters. All right, so what I'll do is I'll just say, all right, for the triangle part, we know that the distance traveled equals 1/2 times base times height, so 1/2 times t, and then the other side of that triangle is 1.8 t. Okay, plus the rectangular area is a 20 by t rectangle, so it's just 20 t. All right, so we've got the area of the triangle plus the area of the rectangle, and we know that that together has to equal 1,000. Okay. Then we're just going to simplify to get that all on one side. All right, and so what I end up with here is 0.9 t squared plus 20t minus 1,000 equals 0. All right, and then what you can do is you can do the quadratic equation on this. It's negative b plus or minus the square root of b squared minus 4ac all over 2a. And you can figure out what t is from that. I would recommend reviewing that process on your own if you need to. But what you should get from that is that t equals 24 seconds. All right, now we're not quite done because it didn't ask for t. Well, it said how long does it take and how fast would it be going. So this is just one of our two answers. So 24 seconds is how long it would take. To figure out how fast it would be going, what we can do is we can go back and look at that delta v. Again, the delta v is 1.8 times t. So we can say our final velocity, which I'll call vf, equals our original 20 meters per second, that's our original velocity, plus 1.8 times our time, because it was getting 1.8 meters per second faster each second. So 1.8 times 24. All right, and then you calculate that, and you should get 63.3 meters per second for your V final. Okay, going on to these really actually pretty confusing and hard problems on the back. What we're given here is a high-speed train travels down a track with a speed of 40 meters per second. The conductor sees a cow on the tracks, applies the brakes to achieve an acceleration of negative 5 meters per second squared. If the cow is 100 meters away, how fast is the train going when it strikes the cow? So in this one, we have an initial velocity of 40 meters, all right, but it doesn't actually slow all the way down to a stop, all right? We're just slowing as we're getting closer to the cow. We know the cow is 100 meters away. So what we do here is we're going to have another one of these things where we have multiple areas here. This right here is your change in velocity, all right? This is your change in velocity, which equals acceleration times time. So in this case, the side of that, its acceleration is 5 times our time, which we don't know what it is. So this side here is 5t. Now, underneath here, this little area is 40 minus 5t, because whatever's left over that wasn't included in that change in velocity section, that first top part, has to be in the bottom. So we have side lengths of 5t and 40 minus 5t for the rectangle and the triangle, and then this here is t. All right, so for some unknown amount of time, the train is moving forward. We're losing 5 meters per second of velocity for every second that it's going forward. So there's where the 5t is from the change in velocity, and then whatever's left is on the bottom there. And so then what we do once we have this set up, and I'm just going to clarify, some things over here on the side. Just to make it look a little neater, I'm just going to call this 5t. All right, again, remember that was our change in velocity. And then over here on the bottom, this is the remainder. 40 minus 5t is this spot here. It's like what it is on the side of that rectangle. 40 minus 5t. Alrighty, and so to calculate the area of this, we've got two shapes. We've got the triangle and the rectangle. For the rectangle, it's 40 minus 5t times t, and then plus the triangle, 1/2, and then the sides in the triangle are 5t and t. All right, that's the whole area there. We just need to now simplify it because we know that this has to equal 100 meters because the area is the distance traveled, and we know the cow is 100 meters away, and we're trying to find information about when it strikes the cow, so this all has to add together to be 100 meters. So what we end up with here is just distributing that t through, 40t minus 5t squared, all right, plus 2.5t squared. That's the simplification of the second part there, equals 100. All All right, and then combining like terms and bringing everything to one side, we end up with 2.5 t squared plus 100. Well, we'll do minus 40t plus 100 equals 0. Then you can do the Pythagorean theorem on that, the quadratic equation on that, and you should find that t in this case equals 3.1 seconds. Once you have that, you can plug it in to find the final velocity. V final, we're going to take our initial velocity, all right, which was 40, and subtract away what's missing, minus that 5t, so minus 5 times the 3.1. And what we end up with here is 24.5 meters per second. Okay, that one is quite tricky. So just to let you know, this would be like a challenge problem on a test for extra credit. It probably wouldn't be anything that I'd ask you to solve on your own. This one, pretty highly tricky, but if you understand what's going on here, you're in pretty good shape. Alrighty, for this second one, it's actually very similar. So since an object is thrown straight up into the air, the initial velocity is 20 meters per second. In the upward direction, assuming that the gravity creates a downward negative acceleration of 10 meters per second, find the two values where the object would be at a height of 15 meters. So for this one, what we're doing is we have an initial velocity of 20 meters per second, right? And it's going to be getting lower as time goes by. And what I want to know is the two times when it is at 15 meters. Now, here's kind of a trick. It's going to be like at some point here, right, where it's going up still, right, and we're going up through this whole place. And eventually, it hits its peak, and then it starts coming back down again, which is like over here. And so what ends up happening is if you throw something in the air, it will go up, and then it will come back down again. It will pass through the height of 15 meters twice, once on its way up and once on its way down. But what's nice is we can actually get an equation from our original situation that will give us both of those times. And I'll kind of explain to you how that works as we go through here. So this is 20. As I said, the setup is very similar to the last one. So we're going to have we're going to lose some velocity here. So 10t is on that side. And then the remainder here, 20 minus 10t, is what's left on the bottom. All right, similar to the logic on the last one. And so then you can create an equation here. The time, again, of course, across the bottom is t. So we create an equation here for the area. I get 1/2, this is just for the triangle, times 10t times t plus the rectangle. This is t times 20 minus 10t, all right, area of the rectangle. And we know that this has to equal 15 meters because that's the distance that it travels. I said find the times where it's 15 meters away or it's traveled up to a height of 15 meters. So that's the area, all right. So we simplify this, we get 5t squared plus 20t minus 10t squared equals 15. Combine like terms, bring everything to one side. We get 0 equals 5t squared minus 20t plus 15. And then if you do the quadratic formula, or actually you can just factor this one if you wanted. But you should get that t equals 1 or t equals 3. And that actually gives you both of the solutions. So remember I said it was going to pass through on its way up, and then it would pass through again on its way down. Well, these are both of those solutions. So t equals 1 or 3 seconds. All right, and that is the answer to this one. All right, I know that that's all pretty complicated. Remember again that the quiz is going to be mostly like questions 1 through 4 on this. Questions 5 and then the 2 challenge ones on the back are mostly like extra credit type problems. They're pretty challenging, but hopefully you'll have a pretty good understanding of a lot of these, and then when you go into the test, it should seem easy because it's the easier problems that we're doing on the quizzes and on the test for this. If you have any questions about any of these, please make sure to stop in and ask. If you did not watch the other video on doing velocity versus time graphs for these acceleration problems, watch that one too. If you watch both of these videos together, I think that it should help get you pretty sorted out in terms of these graphs.